This is the era of the super insulation. Started in sort of the late 70s, 76, and just died in 86, and you'll see why. Okay, it's an amazing history. All right, so what happened here was, well, actually, let me go back. This 1975, so 74, oil prices, lines, embargoes, prices go up. Immediate response, 1975, the corporate, automotive fuel efficiency standard, okay, doubled efficiency standards. Great response, and that was the beginning. Okay, Jimmy Carter came in. He, in 1970, he actually created the Department of Energy. He formed it, including NREL, okay, one of our leading institutions on energy now. 1978, the National Energy Act, all sorts of incentives for energy efficiency, renewables. He was basically, creating incentives to get sensible about energy. 79, I don't know if you all remember, solar panels on the White House. Okay, great. There's the photo op right there. And in 1980, the Energy Security Act, more things. Lots of incentives and so forth, as of 1980. Okay, and that was sort of like peak oil. Well, guess what? They actually worked. Prices started coming down as fuel efficiency and everything, but we had a change of policy, if you will. So the Reagan administration came in and basically during the entire course of the 1980s defunded all of the activity that had been previously built up. In fact, in 1982, they submitted a bill in the Congress to actually eliminate the Department of Energy. Now, luckily, it failed. It didn't pass, but that was the idea. 1986, the solar panels were ripped off the White House, right? And the actual MPG standards that had been previously established and doubled were actually lowered. We went backwards. Okay. All right. Now, so super insulation, you can imagine, with this going on, just died. Nobody cared, right? Now, I say almost forgotten because luckily they were paying attention in Europe. And along comes Dr. Wolfgang Feist and some colleagues, okay, in Germany, a German physicist. And he said, oh, this is too good to not use this. So they started, this is where the term passive house, it comes from Passivhaus, right? And he was applying about the use of passive thermal energy, okay? He actually created the first one in 1992. Lots of design work ahead. By 96, they created an institute, which now has how many scientists? 56 scientists working on Passive House in Germany, okay? 2004, there was a German student who came to the US and actually built the first model Passive House in Illinois. And closer to home, here in Willow Glen, 2012, the first net zero energy Passive House in California. Okay, so it survived. And what happened in that, when Dr. Feist and they took it up, Germany, what they did was they articulated the problem. Okay, good German, physics, right? Right? They created an equation. They formulated the problem, okay, in the correct way, right? QS plus QI minus QT plus QV equals QH, right? Which is simply passive gains minus passive losses, right, equals active energy demand. So that's how much fuel you have to burn to keep the building at temperature. So another way to look at this, we think about energy balance, okay? We're thinking about thermal energy, of course, and we're thinking about a building which is basically a thermodynamic system, right, that has gains and losses, some of which are passive and some of which are active. The passive ones, we have QS and QI, so that's the solar gains and the internal gains. Got a lot of internal gains going on here, right? Right? Okay, those are being added passively to the building, and then we have losses through the envelope, through the windows, through any kind of leakage and infiltration, which is QV, okay? And then the balance is kept in the winter by adding heat, right? And in the summer by removing heat, okay? QS plus QI, there's the equation. Okay, no one had ever bothered to actually formulate the equation of the problem before, okay? Once we've done this, once they did that, oh boy, that's an oh my God, right? When I understood it, that was my response, oh my God. Why? Because now we have a framework to actually design, model, and build buildings that really perform. There's the equation. So now our transmission losses, our QT, the basic fundamentals of that, insulation levels, thermal bridging, quality of windows and doors, and so forth too. We adjust those, right? And that affects that variable. Ventilation losses, so air sealing, make the building to a certain tightness level, and we control the infiltration and exfiltration of heat and air. We can use a heat recovery ventilator of a certain standard to, again, to minimize those losses. We get over to the gain side. QS, okay, the location, shape, orientation, glazing. Here's where sort of the old passive solar ideas come in. There's passive thermal energy. Let's take advantage of, let's design to that. And then finally, internal gains, we can model all this because everything that we use in here is, including the bodies, we're generating heat. So we solve the equation, okay? And we get, as building designers and scientists, we just adjust these variables, right? And boom, we come up with a solution. So, the second thing one of the things on the list is the tool. Okay, that's all very well, right? I mean, all those equations and everything. Well, this, okay, is the Passive House Planning Package. A few screen captures. It's an Excel spreadsheet of all things. It was first done in a full simulation model, and they realized, well, that's never going to cut it because nobody's going to be able to, take the time to put the inputs. So they very cleverly, over the years, figured out a way through lots of testing and so forth to flatten the model, if you will, and put it into a spreadsheet, and it works brilliantly. Okay, 25 years of testing and tuning and verification. Okay, so there's all sorts of things, and like these are windows and all sorts of values. There's climate data. There's all sorts of things.
Quick question?
Yes.
So is that model actually doing 87, 60 hours and doing that thermal balance hour per hour to a typical?
No, it's using constants. It's run, and they develop constants against the model because they realize the problem. They want guys like me to be able to use it and to use it quickly and efficiently.
So for peak heating or peak cooling days, you could still be pretty far off, though, right?
Well, but you're actually dealing with a super insulated building, and it just completely flattens those curves, and that's one of the secrets to it. Okay, it has.
Transmission losses and heat gain, are those per square foot?
That's for orientation. That's specifically Windows. Okay, and I'm just going to do this really quickly. So it has comprehensive variables, really detailed thermal energy flows by variable and subvariable and so forth. It predicts energy loads, and it basically solves the energy balance equation. Now, it's big. Can be intimidating, but it's actually pretty straightforward. So here's the 36 different, or some of the tabs. Climates, U values, areas, what the ground is like, components, window shading, ventilation, and then we get some of the energy balance for the heating season. We've got all the cooling stuff in there, including all sorts of passive cooling energy strategies, all sorts of other worksheets on electricity, thermal gains, and so forth. It's a big model, lots of pretty colored tabs. It does things like this, so R values, or U values if you're using standard international units, you would simply define, like, here's an external wall, here are the basic components of that assembly, their different R values, any secondary, like in the framing in a frame cavity, how thick they are, boom, and we get total R values, and of course we tune all these. How many inches of insulation are we using, etc. And this is typical of many, many other kinds of things. And then we start getting more visual representations, like this is monthly heating demand by month, and we see, for example, in January here, this yellow, okay, that is the passive, that's solar and internal, okay, and the blue line is the transmission losses. So we see, in order to have a balance there, we have to add heat, okay? We get verification metrics to meet a standard in US terms. 4.75 kilobtu's per square foot is a standard. 0.6 air changes per hour, really tight is that. Different and we get these standards. I'm not going to take too much time. Yes, sir.
Like single-family residential buildings?
Can be used in any type of building. Any building is being used extensively for commercial and institutional in Europe, including office towers. It's amazing. Now, energy balance, again, as I said, is the single most elegant simple, useful concept in there, the balancing gains and losses. And you can see in the newer versions, we're constantly giving you visual feedback as to what the thermal energy balance in your building as it's been specified. So you see here this bar chart of the losses and the gains are pretty obvious. They use color. So this is going to be gains from solar, right? And this is going to be internal gains, right? And the red is the difference that has to be made up. This was like January, or this is the total. The red is heat, but it's always in balance, right? And then here, your transmission losses from the walls, and this is going to be the roof and the floor, and windows. Windows are a big one. So always this concept extremely useful, so you can tweak and tune and do these sorts of things.
Are these based on different climate zones?
Ah, yes. All very climate zone specific. And the climate data just keeps getting better and better all the time, data sets. Okay. So we have a great, we have a great tool and a great concept to work with. All right? That's the background. And that's what we drive the spreadsheets, among other things, and so forth. So that's the introduction. That's the background of building performance and where we are. We know we don't have a very, our building culture doesn't really, at this point yet, value performance that much. It's changing, hopefully, and hopefully with Passive House and some of these principles and tools, we'll get better at it. So now we have two of the projects that we've done at One Sky Homes that we've actually designed and built. One is a new build and one's a retrofit. And the new build we'll look at, we have 2 years of data on that, and this other retrofit we have 1 year. And again, we partner with the U.S. Department of Energy's Building America program, and they have all the data loggers and the monitoring equipment, and they do all the analysis and the graphs and charts, thank goodness. Yeah. So we're going to talk about those and show you data, and we can go really deep or we can start skimming along, because there's some very interesting stuff if you are interested in that kind of stuff. All right, and then we'll stop, and then David can introduce all the people, and we can go talk about the Magic Project, which you get to actually feel and touch and walk around. Okay. How are we doing on our pacing?